So today's topic is perturbation theory. Okay, so till now what we have discussed in the series of the quantum mechanics lecture is nothing but the introduction of quantum theory. As we have already noticed that the 1900 was a very important and crucial year for the physicists, as because from this year the new branch of physics known as the quantum mechanics, or the new kind of approach, was introduced in the year of 1900 by the introduction of Planck's law of radiation. So what Planck assumed, that Planck assumed the energy is not at all a continuous in small level system, but it is some discrete quantity and can be expressed as E is equal some nh nu, and the radiation emitted by a black body can be considered as a collection of a independent linear harmonic oscillator. Okay, so this was his assumption regarding the black body radiation to satisfy the experimental graph with the theoretical graph, and he successfully explained these two. Next, by the application of this uh, discretization of energy, Einstein approached the photoelectric effect and successfully explained the Hertz uh, assumption, which he was assumed but cannot prove. But by the application of quantum theory, Einstein was able to give the satisfactory explanation regarding the photoelectric effect. Next, Compton effect was originated. From this we have uh, come to know about the particle nature of radiation, and all of these are accumulated and we get the uh, wave particle duality, in which the wave can behave as particle as well as particles can behave like wave, and from de Broglie hypothesis we can easily prove them, and Davis and German experiment gives this experimentally proof. Experimental proof was given by Division and German. So next, in the year of 1925, Schrodinger come into the picture and give the beautiful mathematical equation, which was a basic equation for the quantum mechanics, and we started the study of quantum mechanics by the use of this equation, this fundamental equation, and come to know about what is wave function, what are the eigenstate, what are the wave eigenfunctions, and many properties of them have been studied till now. Next, we have applied this Schrodinger equation to many problems where the potential was assumed to be constant in somewhere. That is the first application of uh, Schrodinger equation was based on the box problem. The first application of Schrodinger equation was based on the box problem. Just a second. Something went wrong. Okay. Yes, this was the first application of Schrodinger equation, where we have assumed the quantum particle is trapped inside a potential box where the potential inside the box is 0 and outside the box the potential is infinite. Next, we have find out the solution of the Schrodinger equation by applying the boundary condition, which should be satisfied by a well-behaved wave function, and we approach the energy eigenvalue as well as the energy eigenfunction. Okay, So this was the energy eigenvalue in equation 7. And this was the energy eigenfunction. This was the first application of the Schrodinger equation. Next we have considered the step potential problem, where the potential at some region is 0 and at some region it is finite. Suppose V0. Here also we have solved the Schrodinger equation and get the energy eigenvalue, as well as some interesting properties such as tunneling. All these things had been discussed in detail. Next we moved to the problem of potential rectangular potential barrier, where the tunneling become very clear, and we have noticed the important application of this rectangular potential barrier in nuclear physics in explaining the alpha decay problem. Okay, this was very simple to calculate. Again, another application was based on the finite square wave potential, where the potential was assumed to be finite, and it was very similar to the uh, infinite potential box, but here the potential is finite, so it is called finite square wave. Here also we have solved the Schrodinger equation and get the energy eigenvalue as well as energy eigenfunction. So the one thing is common, we have to solve the Schrodinger equation to get the energy eigenstate as well as energy eigenvalue. This was the main purpose for discussing the previous lectures. Okay. Next we have considered the general potential, most general potential, where the potential is the function of x square. Okay, the potential was assumed to be a function of x and it is related to x by x square. That is, if we consider the simple harmonic motion, then Vx is nothing but half kx square. And by putting this potential in the Schrodinger equation, obviously time independent Schrodinger equation, as because the potential is independent of time, so we get the solution here also, and we can easily determine the energy eigenstate as well as energy eigenfunction. All these things have been derived in detail in the previous lectures. These are not at all the purpose of today's lecture. Okay, but I want to recapitulate you what we have done till now. The next one was based on the central potential problem, where we have solved only the hydrogen atom, not hydrogen molecule. This was the simplest among the central potential problem, so we are very much interested to solve this. Okay, after certain modification we can get many other problem also. So by the introduction of the Schrodinger equation in the central potential problem, we consider this in spherical polar, as because the atom is simply assumed to be spherical in shape. So the study of Schrodinger equation becomes simpler in the spherical polar coordinate, and we have already derived the radial part as well as the azimuthal part and the angular part. All these things have been derived. Okay, successfully. So these are the old application of the Schrodinger equation. Not old application, this was the simplest application of the Schrodinger equation, but unfortunately I must have to say that quantum mechanics is not at all the simple thing, as because many problems are present here which cannot be solved very simple in very simple way, like that we have already derived. Like the potential is not constant, the potential is not at all a function of only x square, the potential is not at all depends inversely to the r. It may vary with r in any power, it may vary with x in any power. and it not at all a constant, it may have some complex structure. So the solution of the Schrodinger equation becomes very tedious and very difficult in that case. So the Schrodinger equation becomes very difficult in general to solve. To solve many problems. Okay, many practical problems. Many practical problems. By what? By exactly. This word is very important. We cannot solve the Schrodinger equation exactly for these practical problems like the uh, like the quantum mechanical problem of helium atom or the other kind of atom, which is very much complicated from the hydrogen atom problem. So the solution of the Schrodinger equation for that case becomes very difficult, and we cannot get the exact solution by the application of the Schrodinger equation. We have to overcome this problem by what? By assuming the approximate solution. Approximate solution. Okay, by the approximate solution of the ideal problem, or with the help of these ideal problem that we have solved till now, we can solve this difficult practical problem. But we cannot solve this problem exactly. We can solve them only approximately. There are many approximation methods. There are many approximation methods present to solve the practical problems related to the quantum mechanics, out of which we can list them. First, which is the perturbation theory. Second thing is WKB approximation. And another method is variational principle. Variational principle or method. Variational principle or method. Out of which we only emphasize today the perturbation theory. So let's start the today's discussion, which is based upon the perturbation theory. So what we have learned till now, that we have solved many problems, many simple problem where we can easily solve the Schrodinger equation and get the energy eigenvalue as well as the energy eigenstate. But in certain problems, like the practical problem, like the solution of helium atom, sodium atom, etc., where the solution of Schrodinger equation becomes very difficult, we can only evaluate the approximate solution, not the exact solution. Okay, so there are many approximation methods present till now, which are perturbation theory, WKB approximation method, and the variational principle and method. Now you can ask me that how to know which method is applicable to which. This is very important question to know. Uh, all these three methods have different applicability. The perturbation theory is applied to the system where the potential is slightly distorted from that of the ideal case. So, by the applying the knowledge of the ideal case, by the applying knowledge of the ideal case and the applying solution of the ideal cases, we can approximate the solution of the perturbed case. By the word perturbation, we mean that it is nothing but the disturbance applied to a system. Disturbance applied to a system. Let me check. Okay. So perturbation means nothing but the disturbance applied to a system, to a ideal system. So by assuming the solution of the ideal case, we can modify the solution and approximately guess the solution of the perturbed case. So without wasting any more time to the introduction, I am going to discuss the main uh, theory regarding the perturbation. Okay, at first you have to differentiate what is a perturbed system and unperturbed system. I have already mentioned that perturbed system is what, when some disturbance or some conditions are applied to the ideal case so that we cannot solve the Schrodinger equation directly there, are known as the perturbed system. And by the unperturbed system we means the system which we have already solved in previous lectures. So at first you have to differentiate what is perturbed system and what is unperturbed system. Unperturbed system. Sometime you may ask to define what is perturbed system, what is unperturbed system, and you can easily define it. So we are interested to discuss the perturbed system here, which is different from the unperturbed system. By what kind? I have already told you. Okay. Now let us picturize them. I have defined these by the language. So let us see how this perturbed system can be defined. So by perturbation we means we have already studied the box potential problem where the particle such as quantum particle may be assumed to be within a potential box where the potential is 0 in certain region of box length, suppose 0 to L. So box length is L and the particle is trapped inside the box, and outside the box the potential is infinite. So it may be called the infinite potential box. Okay. So by the word perturbation we can solve easily this type of problem as derived in my previous lecture. But if you are asked to solve the same problem where the potential base potential have introduced certain bumpy region, sorry, okay, the potential contains some bumpy region here. Okay, so you have to solve the problem now. So obviously you cannot solve this problem as previously done. You have to modify the solution of the ideal system so that you can approximate this problem, the solution of this kind of problem. So let me move on to the problem where I can explain you how can we approximate the solution from the ideal case. So in the previous ideal case, what we can write, the Schrodinger equation is nothing but H uh, okay shine 0. Okay, for the uh, nth state, we can write the time independent Schrodinger equation like this, where the H cap is nothing but the unperturbed Hamiltonian of the system, Hamiltonian operator of the system. Shine 0 is the unperturbed eigenstate. Okay, En is the unperturbed eigen energy, eigenvalue, and where n can be 1, 2, 3, and so on. Now I have introduced the exponent here. What does it mean? It means nothing but the unperturbed state. This is not at all power, so that I put it into the bracket like notation, so that you can differentiate what is power and what is exponent. It is nothing but only the mode of representation. It is not at all power. Okay, so h cap psi n is equal en psi n, where n is equal 1 to 3. This is the eigenvalue equation for the unperturbed state. Again, the shine 0 is the wave function of the unperturbed state or energy eigenstate. So this can form the orthonormal state, as we have discussed already in the previous sections, where we have discussed the properties of wave function. The quantum mechanical wave function can constitute the orthonormal set where shine 0, 0 means only the unperturbed state. Okay, shine 0, 0 and 1, 0 when n not is equal m, and when n is equal m, this becomes 1. I have written this in bracket notation. If you may write it in integration format like this, psi 0 star, okay, psi m dx. You can write this in integration format also, but in this lecture we mainly focus on the bracket notation, so you have to make a clear understanding of this. This means some bra notation and this means some ket notation. It means the simple wave function psi, but it means the complex conjugate of psi, which is psi star. This is the ket notation and this is the bra notation. For details, you may consider a book, Zetley or Griffith, whatever you know. Okay, so let's move on further. What we have discussed till now is nothing but the eigenvalue equation for the unperturbed state and put it as equation 1. Now, if we perturb the potential energy slightly from the unperturbed state, okay, what I've done, So this was a unperturbed state eigenvalue equation. But if we perturb the potential energy of the system slightly from the unperturbed state, that means if we apply some small perturbation in it, then the solution of the perturbed system can also be written from the eigenvalue equation. This, but here it is perturbed, so we disqualify the zero term here, simply meaning the system gets perturbation. So this system can be modified to this by the introduction of perturbation in it. Here also n is equal 1, 2, 3 and so on. Okay. Now H cap is the perturbed Hamiltonian operator here, and En is the perturbed energy eigenvalue, Psi is the perturbed energy eigenstate. Now the theory of perturbation lies here. We can simply write the perturbed Hamiltonian, the total Hamiltonian of the perturbed system, as composed of H0 plus some lambda H prime, where H0 is the unperturbed Hamiltonian operator and H prime is the perturbed Hamiltonian operator. Hamiltonian applicable to the perturbed state, and by adding these by the introduction of lambda, we can get the total perturbed Hamiltonian of the system given. So let me specify the term introduced here. H0 is the unperturbed Hamiltonian and H bar is the perturbed part of Hamiltonian for perturbed system. Okay. Now what is lambda? Lambda is nothing but a parameter, and it can change from 0 to 1. Now let's suppose the lambda is 0. So what is possible from here? The total Hamiltonian operator of the system becomes equal to the unperturbed. So there is no perturbation present in the system, and the total Hamiltonian is nothing but the unperturbed Hamiltonian of the system. But if the lambda becomes 1, then H cap is simply H naught plus H prime. So there is full perturbation present in the system, and if some small fraction, then the amount of perturbation can be determined from the lambda. So we can easily draw conclusion from this that the amount of perturbation can be known. What amount of perturbation present in the system, is it small or large, can be determined by the factor lambda. So lambda is nothing but a parameter which may have the value from 0 to 1. Change from. Okay. So this, put this equation as equation 2. Okay. Okay, the condition is given as equation 2, and this equation is written as equation 3, and um, this can be written as equation 4. Okay, now on the basis of lambda, that is the amount of perturbation present in the system, we can expand the energy eigenvalue En and energy eigenstate psi n, just similar to the Taylor series. In Taylor series, what we can do, f x plus h is nothing but some fx plus h f prime x 1 factorial, h square 2 factorial, double prime x, and so on. Okay, so this was the Taylor series. Just like similar, we can approximate the energy eigenvalue of the perturbed state and the energy eigenstate of the perturbed state, like En is equal En 0 lambda En 1 lambda square En 2 lambda cube En 3. I put the exponent of En within the bracket to differentiate it from that of the power. Here power is present on lambda, but the exponent of E does not specify or does not signify the power of E. It only specifies what is the order of the perturbation. So En0 means the unperturbed energy eigenvalue, and En1 means the first order correction in energy eigenvalue. En2 is nothing but the second order correction to the energy eigenvalue, and so on. Like in a similar way, eigenstate can also be write these, and so on. Okay, namely it as equation 5, 4, 5, equation 6. Okay. So all the things are within our hand, and we have to apply them in the equation number 3. So let me write another term also here to make the similarity with En. Lambda cube En, sorry, psi, and so on. Okay, so all the things, okay, just remember this. En0, what does En0 signify? En0 is nothing but the unperturbed energy eigenvalue. This means unperturbed energy eigenstate. Okay, psi n1 means first order correction to energy eigenstate. Psi n2 second order correction to energy eigenstate. Psi n3 third order correction to energy eigenstate, and similarly the terms of En can also be written as, just a second. Okay, so En1 means, En2 means okay, En3 means, so En1 is first order correction to energy eigenvalue. Just we have to change these as second and these as third. Okay, these are the term mentioned in equation 5 and 6. So put these terms or equation 5 and 6 in equation 3. Remember what is equation 3? Okay, let me copy this. This was the equation number 3. So we have to let again copy this. Here. Okay. Okay. Put the value of E in here, put the value of psi in here and here. And put the value of H from 4. From 4, put the value of H. So by incorporating these values, we get H0 plus lambda H prime. I here ignore the cap, but you may as well write the cap here. Writing the cap is very logical, but I here ignore to write the cap notation just to make it clean, otherwise it becomes so clumsy. But the logical is to write the cap notation, so let's do it. Psi n 0 plus lambda psi n1 lambda square psi n2 so on is equal nothing but en0 lambda en1 lambda square en2 and so on into psi n0 plus lambda psi n1 plus lambda square psi n2 and so on. Okay, so at first multiply by h naught cap to this equation, then to this. At first you have to multiply en0 to this, then you have to multiply by lambda en1 to this, then you have to multiply these to this. So after certain simplification and multiplication, you may write 0 sin 0 plus lambda h0 sin 1 plus lambda square h0 sin 2. Okay, this is done. Now the time is to multiply this. Okay, so on plus lambda h prime psi in 0 plus lambda square h prime psi in 1 plus lambda cube h prime psi in 2 so on is equal e in 0 psi in 0 plus lambda e in 1 psi in 1 plus lambda square okay e in 0 in 0 psi in 2 plus dot dot so on plus this term okay lambda e in 1 psi in 0 plus lambda square e in 1 psi in 1 so on plus lambda square e in 2 psi in 0 plus lambda cube into psi in 1 plus dot 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 okay this is very long expression but you have to simplify it by your own way of simplification method okay now the main purpose of writing this is to equate the coefficient of lambda okay so okay this term in the left hand side and this term in the right hand side are independent of lambda or we can write that this is the coefficient of lambda to the power 0 so you can write it as lambda to the power 0 so by equating the coefficient of each power of lambda we can get h0 psi 0 is equal e n 0 psi 0 put it equation number 7 okay let me check yes after 6 this is the equation number 7 now equate the sorry now sorry now equate the power of lambda the coefficient of lambda from left hand side is this and from the right hand side this and this okay so comparing the coefficient of lambda square we get h0 psi n 1 plus h prime psi n 0 is equal sorry 0 psi n 1 plus en 1 psi n 0 okay and name it as equation number 8 now it is the time to compare the coefficient of lambda square from this and this of left hand side, and this, this, okay, and as well as this. These are the two terms present in the left hand side, the coefficient of lambda square, and these are the three terms present in the right hand side, the coefficient of lambda square. So equating these, we can write E0 sin 2 plus H prime sin 1 is equal to nothing but En0 sin 2 plus En1 sin 1 plus En2 sin 0. Name it as equation 9. Okay. Now, till the theory that I have discussed now, whatever I have discussed, we are not interested is the system about the thing that the system is degenerate or non-degenerate. Now, what is degeneracy? Okay, you know this, but I want to recapitulate you. So there are two possibilities. First is degenerate, and second thing is non-degenerate. You have learned it in the discussing 3D potential box and in discussing 3D harmonic oscillator, as well as in discussing the hydrogen atom problem. What is degeneracy? So here I only want to give you the definition, that is, if the eigenvalue equation be satisfied by more than one eigenstate. Okay, let us write this. This is the eigenvalue equation for a net state, but if this equation is also satisfied simultaneously with this, then there lies a degeneracy between them. Here lies the degeneracy, as because the eigenvalue equation is satisfied more than one wave function present in the system. But in case of non-degeneracy, different eigenstate gives different eigenvalue equation. This, but if we apply psi m, then it gives another eigenvalue. So another eigenvalue and return the eigenstate. So this is the case for non-degeneracy, and this is the case for degeneracy, where the eigenvalue equation is satisfied by more than one wave function. But here only one wave function satisfied one eigenvalue equation. So we have to differentiate the above theory into the two classes. First one is non-degenerate case, and the second one is degenerate case. Okay, I have forgotten to differentiate the perturbation theory also. Okay, sorry for that. The perturbation theory, okay, let me create some space here, as because it is very important to discuss in this context. Okay, I think yes, This is sufficient. um, okay, so the perturbation theory are of two types. Perturbation theory are of two types: time independent perturbation theory and time dependent perturbation theory. I mainly considered the in the first lecture that time independent perturbation theory. Time independent perturbation theory is different, where the perturbation depends on the time as well. But here I assume the system, the perturbed system, where the perturbation does not depend on the time at all. And the things what I have already done is nothing but the on the basis of time independent perturbation theory. So please create some space in between them and add this thing also in your class note. Okay, now let's back to our discussion. So I have to specify is the system is non-degenerate or is the system is degenerate. Here for simplicity, in the first lecture, uh, as because this is the first lecture on the perturbation theory, I mainly consider the non-degenerate case. It means different eigenstates satisfy different eigenvalue equation with different eigenvalues. Okay, so for the non-degenerate case, let's proceed on further. Let's write the equation as written in this. So this becomes E1 0 psi 1, and uh, we can write another Hamilton eigenvalue equation for psi 2 also, another wave function. So this gives another eigenvalue with the same wave function. Okay, these are the eigenvalue equations satisfied by different wave function for different eigenvalues. Sorry, this is E2 and H0 psi 3. So this will be this and this and so on, so on. Okay, so you can write from equation 8 that H0 psi n1 plus H prime psi n 0, I think 0 is equal en0 psi n1 plus en1 psi n0. Okay, so in kit notation you can write psi n1, just put the kit symbol here. In kit notation you can write this. This what I want to find. I want to find the first order energy correction. We can also find second order energy correction, but uh, you can say that all the correction can be determined from this, and but uh, what limit we can determine the correction of energy, that is what uh, fourth order energy correction, fifth order energy correction, sixth order energy correction and so on energy correction are possible, but up to which we can calculate, we can calculate each of them, but this becomes very difficult. You can notice here that by determination of En1, this is a simple thing. Okay, the determination of En1 is rather very simple, but when we are calculate the second order energy correction En2, the solution becomes very difficult, and the form of the second order energy correction is also very difficult. Similarly, the difficulty will increase on proceeding further order correction of energy. That is, the third order energy correction becomes more difficult, fourth order becomes more difficult, and so on. So up to second order energy connection is enough for us to evaluate the perturbation and approximate the energy of eigenvalue of the perturbed system. So at first you have to understand how to find the first order energy correction so that you can able to find out the second order energy correction and so on. So let us find out the first order energy correction from this. Similarly, you can calculate the first order wave function correction, SHINE1. Similarly, you can find out the second order energy eigenfunction psi n2 and so on. But the solution of psi n1 itself is very complex, and when you are going further to calculate psi n2, this form becomes very difficult to accommodate. So after studying the form of psi n1, you will notice that why I am saying so. So let us first derive the expression for first order energy correction. So till now I have nothing done the mathematics involved here. So from this only the Kate notation have been introduced, nothing changes have happened. Now let's multiply the whole equation or the above equation by Brassai in 0, that is the unperturbed wave function, complex conjugate of the unperturbed wave function. Now why I am multiplying this, as because there is a property psi n0 bra psi n0 Kate psi n1 gives always 0. Similarly, bra psi n0 Kate psi n0 gives 1. Just similar to the orthogonal property where psi m gives 0 for n not equal to m, and psi n gives 1. Okay, just similar to that, it is easy to remember by the similar approach, but it is different thing. The order of order of correction is present here to differentiate sin 0 and sin 1. These are the same eigenstate, but this is eigenstate for unperturbed state, unperturbed system, and this is the first order correction of the wave function for init state. So by multiplying we can get psi n0 get bra psi n0 is 0 get psi n1 plus bra psi n0 h psi n1 is equal psi n0 en0. This is not at all so difficult thing to do. Psi n0 en1 psi n0. Okay, so this is constant term, so this can be given out of there, and we can write this as this plus of, okay, similarly you can also take en outside there and simply write this. Okay, now this thing is 0 from this, so we can write it as en 0 into 0 plus en, this thing becomes 1 from the property, so en 1 into 1. Again this involve different state. So the expectation, it means the definition of expectation of H0. So this cannot be determined because the states are, sorry, the order of sign are different. It is a perturbed, unperturbed wave function, and it is a first order correction to wave function. So the expectation value of H0 here is 0. This is nothing, this is not at all expectation, but you can think so that the expectation of H cap, but this is not at all the definition of expectation. The definition of expectation is this. This is the definition of expectation, where the order of energy is same, energy eigen state is same. Okay. Okay. So this value becomes 0. On integrating, you can also get the value of this is 0, and only this value retains. So, but okay, this was 0, and this is also 0, and this is also 0. नहीं तो ये भी 0 आ जाएगा. So sin 0 this. So after the tedious calculation, we can get the first order energy correction En1 is nothing but equal to this divided by 1, so called the expectation of the perturbed Hamiltonian. This is the main purpose of discussing the theory. That is, the first order energy correction is nothing but the expectation of the perturbed Hamiltonian present in the perturbed system. So this is the most simplest energy correction. On proceeding further, while determining the second order energy correction, you will notice that this was the this will be not so simple to the first order energy correction. By the calculating or approximating the first order energy correction, you can define the system, what kind of perturbed system you have given. You can make an idea about the energy eigenvalue and energy eigenfunction. So the first order energy correction is most crucial while determining the perturbed energy eigenvalue of the perturbed system. Put it equation number 10. But the thing is not done here. The total energy eigenvalue En becomes equal to En0 plus En1, which means how can we achieve this? As because I have already told you that H cap is nothing but some H0 yes. If we assume the lambda to be 1, then H cap can also be written as H naught cap plus H prime. Okay, so H naught prime plus H prime. Okay, so if we take expectation of this, then you can also get this. And this. Okay, So by applying the eigenvalue equation, you will notice that this is nothing but this, and this is this, equal to h0. So h0 means en0 sin 0 s plus en1 sin 0 this. So this is 1, this is 1, this is 1, and we can get this. So this can be written as en0, that is the unperturbed energy eigenvalue plus the expectation of perturbed Hamiltonian. This is the total energy eigenvalue of the perturbed system. Here we have already only assumed the first order energy correction. First order energy correction. Similarly, you can obtain the second order energy correction, and so on. We can also calculate the first order correction to the wave function. Okay, let's determine the first order energy wave function. So first order correction to wave function, let us derive. Okay, now you already have learned that sin1 can be supposed to be the superposed state of certain sin 0. Okay, so in bracket notation you can write sin1 as some cn. Okay, let me write this as L, general notation. So L. So here also bracket notation will be applied. Now from 8 what we have learned, why I am focusing the 8, because it involves the coefficient of lambda term only, that is the first order correction, and lambda squared, the coefficient of lambda square gives the second order correction. So I only emphasize on the equation 8 to obtain the first order case. What was the equation 8? Okay, so this was the equation number 8. Let me copy it. Okay, yes, this is the kit notation of the equation 8. Let me copy it. Kit form of equation 8. Let me copy it. Okay, paste. Okay, this was the kit form of the equation 8. This kit kit. Okay, now put the summation on both sides. You will able to obtain. I expand sin 1 only. Sin 1 expands sin 1, and nothing to do with it. Okay, so this remains unchanged, and en0 sum CL, okay, and CL 0, okay, and en1 sum CL, and sorry, this is, I think this was sin 0. Let me check. Yes, this is sine 0. This is sine 0. So if this is sine 0, then it remains unchanged. So it remains unchanged. En1 sine 1. So sine 0. Okay. Now similarly multiply above equation by another eigenstate psi m0 from LHS. Then what we can obtain, Cm for all the term other than L equal to m, this will become 0, okay, because of the property mentioned above. If you, okay, let me explain in detail. If you are unable to catch the thing, okay, so Cl and this psi m0 is 0, psi l0, okay, and this psi m0 h cap psi m n0, sum over Cl en0 psi m0 psi l0 plus en1 psi m0 psi n0. This is orthogonal to each other, so this is 0. And after proceeding the series, at the some time L will be equal to m, and for that case we get shim0 and shim0 on the Kate and Bra form. So this becomes nothing but Cm at the value when L is running from this summation to at the position L equal to m. We can write this Im0 is 0 psi m0, okay, and this remains as it is, psi m0 h cap psi n0. Why these are not 0? Because the states are same, sorry, the correction, okay, unperturbed state, in that respect these are same, so this is not 0. But in the previous case, due to the difference of this and this, the previous state was 0. So this is equal to, at the position of m only this value exists, and otherwise this forms the orthogonal set and the value of this becomes 0. So at the position of m only we get Cm En0 En0 psi m0 psi m0, this again this becomes 1. Okay, now this is an eigenvalue equation and we can write Cm Em psi m0 psi m0 plus psi m0 h prime psi m0 equal to Cm em0. Okay, this is En0. This is equal to 1. So we can write Cm common E m0 minus, okay, psi1 em0 plus im0 h cap shine 0. This is nothing but 0. Okay, so Cm is nothing but observing minus sign em0 and here shine 0 h prime shine 0. Okay, this is the value of Cm. This is the value of Cm. Put it as question number 10, 11 number equation. Okay, so we can write psi m1 as Cm psi m0, just like similar as discussed above. Okay, this just similar to above. So for image state this, and this becomes, by incorporating Cm we get sum over m not equal to n. Why? Let's see. En0 minus em0 psi m0 h prime psi m0 into some psi m0. So the unperturbed energy eigenstate into some coefficient and since En minus Em, if n equal to m or m equal to n, then the denominator will be 0 and the wave function becomes undefined, which is not possible. So the summation runs from all the values of m excluding m equal to n. So this is the first order energy eigenfunction. So if we ignore the bracket notation, we get psi m1 nothing but sum over m not equal to n psi m0 h prime psi m0 m0 minus em0 psi m0. This is the equation number 11, 12. But this is not the end. The total expression of the wave function of the nth state of the perturbed system becomes psi n, which is nothing but psi n0 plus psi n1. Okay, I think this was in. As because here the order does not matter, but the summation extends from this. These variables are different. So this is in. So psi n1 sine 0 plus this term. So this is the total wave function of the perturbed state. From this you can easily say or conclude that the first order energy eigenstate correction is not at all very simple. If you assume the second order energy eigenstate correction, then this becomes more difficult from that. So it is enough for our for estimating the wave function of the perturbed state. So first order energy eigenstate, first order correction is more than sufficient. Okay, named it as 13 number equation. Okay, so this is all about the time independent perturbation theory, where we have discussed the first order energy eigenvalue correction as well as energy eigenfunction correction. So in this lecture we have covered what is perturbation theory, mainly the time independent perturbation theory, and derive all the first order correction of energy eigenvalue as well as energy eigenfunction. Okay, this is all about today's lecture. Thank you very much. Don't forget to like and subscribe this channel for more update. Thank you.